Okay, so this will be the second lecture out of Chapter 8. So in this lecture, sort of start out talking about this concept of core electrons and valence electrons. So we talked a little bit about core electrons in the first lecture from Chapter 8. So that's the electrons count corresponding to the number of electrons in a noble gas within the element's total number of electrons. So we'll work some more examples, make sure that makes sense. And then valence electrons will be the electrons that are beyond the core. And so those are the electrons really that are the most important, because those are the electrons that take part in bonding and chemical reactions. So for all practical purposes, the core electrons don't do much of anything besides occupy space. Obviously, they affect the properties of the element, but it's the valence electrons that are the most important, that really chemists tend to focus on, since those are the ones that are participating in chemical reactions and bonding. So we looked at how to write shorthand notation in the last lecture, right? For hydrogen, there's not a shorthand notation. And for lithium, right, that would be its core, so that would be helium. And then 2s1, everything beyond the core. And so for sodium, right, its core would be 10 electrons for neon. And so for potassium would be its 18 electrons. And then if we did the same thing for rubidium, so we looked, of course, in the last lecture how the noble gases, how elements in the same group have the same outer shell configuration. Really doesn't apply to helium since it's only 1s2, but once you get beyond helium, then if you notice the noble gases end in p6. So neon second shell p6, argon third shell p6, krypton fourth shell p6. Okay, so that's its noble. So that would be its noble gas core. That would be its core electrons. So lithium has 2 core electrons. Sodium would have 10 core electrons. And potassium would have 18 core electrons. And then rubidium would have 36 core electrons. And then the electrons beyond the core, would be the valence electrons. So 1 valence electron for hydrogen, 1 valence electron for lithium, 1 valence electron for sodium, 1 for potassium, 1 for rubidium. And if you notice, and we talked about this in the last lecture, what do they all have in common? They are all in group 1. Okay, so we can use this. So once you identify the elements of valence electrons, and you can use that to write what's known as a Lewis dot structure. So that's just the element symbol with enough dots to represent the number of valence electrons. So hydrogen has 1 valence electron, so 1 dot for lithium, 1 dot for sodium, 1 dot for potassium. Okay, so if we did this for fluorine, chlorine, bromine, and iodine, so fluorine's 1s2, 2s2, 2p5, chlorine's 1s2, 2s2, 2p6, 3s2, 3p5. So fluorine, chlorine, bromine, iodine, where are they all at? They're all here in the same group in the periodic table, right? That would be group 7, the halogens. And so from the last lecture, we said that this is P1, P2, P3, P4. So the halogens are going to be P5, and then noble gases would be P6. So if fluorine's 2p5 and chlorine's 3p5, then bromine would end in 4p5, right? And iodine would end in 5p5, would be its last orbital that's being filled. So I've got iodine wrote here, so let's make this easy. Oh, don't cut it, undo that. Let's copy it. And paste it. So bromine then should end in 4p5, so we'll just back this up to the 4p and change that to 5, and that would be 35 electrons. So shorthand notation, again, come on. That would be the noble gas in fluorine, helium. So 2s2, 2p5. And then chlorine, atomic number 17. If you back up to the first noble gas, that would be neon. Right? So how many valence electrons do they have? Well, it's the electrons beyond the core. So that would be, for valence electrons, that would be 7. And for chlorine, that would be 7, right? And of course, what group are they in? They are in group 7. So it's easy to figure out how many valence electrons something has. Just look and see what group it's in. If it's in group 1, 1 valence electron. If it's in group 2, 2 valence electrons. And then we skip the transition metals and come over here to group 3, so 3 valence electrons. 4 for carbon and down, 5 for nitrogen and down, 6 for oxygen and down, 7 for the halogens. Of course, hydrogen only has 1 electron, so it doesn't have 7. It only has 1 valence electron, right? Okay, so for bromine, so the noble gases in P6, with the exception of helium, so then that would be the noble gas in bromine. So 4p6 and then 5p6, or 4p6, right? That would be the noble gas in iodine. So shorthand notation for bromine would be argon, and then 4s2, 3d10, 4p5. Okay, so, but we just said the core, the valence electrons are those beyond the core, and we said the halogens had 7, so how are we going to get 7 out of this? Why isn't it 17? So to answer that question, we need to introduce this concept of pseudonoble gas core. So that's the noble gas core plus the n-1d electrons. So n-1 meaning the outermost d electrons. And so that's going to be, that would be the 3d, right? So we're going to subtract those out. And another way to look at this is the valence electrons would be, you subtract out the core electrons and you subtract out the pseudonoble gas core or the pseudonoble gas core electrons. So that's going to be all of the electrons in full shells plus all of the electrons in filled inner subshells. So what does that mean? So if we look at this for bromine, so the one shell is full because the 1s can only have 2 electrons, right? So those electrons are gone. We don't count them. The second shell is full because the second shell is the 2s and the 2p. So those electrons are gone. Those are part of the core. We don't count them. But how about the third shell? Yes, the third shell is full, right? Because it contains the 3s, 3p, and the 3d. That is full. So we'll subtract those electrons out. And that only leaves 7 electrons. So 7 valence electrons for bromine. And if we did the same thing for iodine, so its shorthand notation would be, so iodine is going to be krypton, and then 5s2, 4d10, 5p5. Again, we have 17 electrons, but we don't count the inner shell d electrons, so that's going to be 7 electrons there. And if we went through the same exercise here, the first shell is full, so we're not going to count the 1s. The second shell is full, so we're not going to count the 2s because the 2s and 2p are full. The third shell is full, right? 3s, 3p, and 3d. So we're going to take those out. What about the fourth shell? Is it full? Well, the 4s is full, right? And the 4p is full, and the 4d is full. Is that all there is to the fourth shell? And their answer is no. There's the 4f as well, but the 4f doesn't have any electrons. So the 4d is a subshell, and it is full. So we're going to take it out. That is right. So we're going to take out all electrons and filled inner subshells. But the fifth shell is the outer shell, so we're not talking about that one, right? Even though the 5s is full, we're not going to take those electrons out because that's not an inner subshell, that's an outer subshell. It's the outermost shell, the fifth shell. So, but we are going to take out the 4d because it's an inner subshell that is full. So that's only going to leave the 5s2 and the 5p5. And if we add those two electrons together, 7 valence electrons again, right? Or the easiest way again is just look at the periodic table. All of the elements in the same group have the same number of valence electrons. Okay, so if we wrote a Lewis dot structure for fluorine, 1, 2, 3, 4, 5, 6, 7 dots, right? Chlorine, 1, 2, 3, 4, 5, 6, 7 dots. Same for bromine, same for iodine. Doesn't matter to me how you write the dots, as long as you got 7 dots. Okay, so how many valence electrons do each of these have? So boron, calcium, and sulfur. So there's the hard way and the easy way, right? The hard way is to look at the noble gas core. And so that would be 2 core electrons, and then that would be 3 valence electrons. So a Lewis dot structure for boron, 1, 2, 3 dots. Or for calcium, that would be its noble gas core. And then, whoa, no, that's not right. This would be its noble gas core, argon, 18 electrons. So then it would have 2 valence electrons. So calcium, right, dot, would be its Lewis dot structure. And then if we did this for sulfur, again, we could do it the hard way. So that would be 10 electrons core. And then this would be 6 valence electrons. So that would be the hard way. The easy way is look at the periodic table. Is there one down here? Yes. So boron is here, that's group 3. Sulfur is here, that's group 6, so 6 valence electrons. Calcium is here, 1, 2, that's 2 valence electrons, right? Okay, so we've been writing electron configurations using this off-ball principle or building up principle using this diagram, right? But the point is here is that this does not work for every element in the periodic table. Some elements have an irregular electron configuration. So we'll just look at a few examples just to illustrate. So if we took vanadium, chromium, and manganese, and wrote their electron configurations, 2 of these is normal and 1 of these is not. So I've given you vanadium here, 23 electrons. So chromium's got 24 electrons. So what would its electron configuration would be? Well, it would just be this with 1 extra electron, so it would be 4d4, right? And then manganese with 25 electrons would just be this with 2 more electrons, so it would end in 3d5. Okay, so chromium is not normal. So what happens here instead is one of these electrons in the outer s orbital is actually in the d orbital instead. So its actual electron configuration, this will fit here. Let's make it fit. So we're going to take one of the s's away and we're going to put it in D instead. So it's going to be S1 D5. So it is not normal. So that's the way it works. So for some of these that are not normal, you take the outer s orbital and take one of its electron and move it into D instead. So why does this happen? So if we drew this in an orbital block diagram instead, so I'm going to ignore the 1s2, 2s2, 2p6, 3s2, 3p6, because nothing's happening to those. I'm just going to look at the 4s2, so opposite spin, right? And so 4d electrons, how would you fill them in? Well, you would fill them in like this, right? You don't pair electrons until you have to because of Hund's rule. So each of those would have 1 electron in them. So, but it's not normal. It's irregular, so one of these electrons is in D instead, so we're going to move that to here instead. So now we only have 1 electron in 4s, so it's 4s1, and we have 5 in D instead, so it's 3d5. right? So 4s1 3d5 and not 4s1 3d4. So why does it do this? It does this because it's more stable to have a half-filled D subshell than a full outer S subshell. So it's all in terms of stability. What is more stable for the element? So in this case here you have 6 electrons of parallel spin. And so that's more stable than having 4 electrons of parallel spin in the filled S subshell. So basically, if an element would normally end in D4, it may not be normal because it may prefer to be S1 D5 instead. So what else might be D4? Well, if you look at the periodic table, here's chromium. So if it's 3D4, then molybdenum underneath that would normally be 4D4, and tungsten underneath that would normally be 5D4. And molybdenum is also not normal. So its outer shell would be, so molybdenum, so if chromium is 4s1, so if chromium is 4s1 3d4 5, then molybdenum would be 5s1 4d5 instead, right? Tungsten is actually normal. Okay, what else is not normal? So the D9s are not normal. So if we took copper, for example, and 29 electrons, if we wrote it out, we would get this. It does the same thing. It takes one of these S's and puts it in D instead, so it's S1 D10. So normal, it would be this. So 9 electrons in the 3D. 4 of them are paired, 1 is not. So what happens instead is one of these electrons in 4s is actually in 3D instead. So you end up with a half-filled S and a full D, and that is simply more stable. So it's more stable to have a full D than a full S. So if you can take one from S and put it in D, then that's what's going to happen. So if copper is not normal, what else would not be normal? Well, copper is here. That would normally be D9. And then below that is silver, and below that is gold. So gold would not be 4D9, it would be 4D10 instead. And gold would not be 5D9, it would be 5D10 instead by taking one of the outer shell S electrons. Okay, so there are many other elements in the periodic table that are not normal, particularly once you get down into the F block, but I'm not going to expect you to know those. I'll just expect you to know these couple of examples from the D4s and D9s, just so that I know that you know that all of the elements in the periodic table don't follow this diagram. Some of them are not normal, right? Okay, so AG would not be normal, and AU gold would not be normal. They would be S1D10s also. Okay, so lastly here, electron configurations of ions. So, let's see. So what charge does sodium typically like to be? It usually likes to lose 1 electron and be Na plus, right? These like to be +1s, these like to be +2s. So fluorines, these like to be -1, right? So it likes to gain 1 electron and be F-. Calcium is here, it likes to be +2, so it likes to lose 2 electrons and be Ca +2. Sulfur is here, these like to be -2, so it likes to gain 2 electrons and be S2-, right? So now we looked at that back in chapter 2, so now we can look at this in this chapter and understand these things in greater context. Okay, so sodium is 1s2, 2s2, 2p6, 3s1. So if it loses 1 electron, which one do you think it loses? Well, it's going to lose the one that's less tightly held by the nucleus, and that's going to be the one in the outermost shell. So that's going to be the 3s1, right? So it's going to lose that electron and be 1s2, 2s2, 2p6. And so then that would be Na plus, right? So what else has 10 electrons? Well, neon has 10 electrons, a noble gas. So by losing 1 electron, now it has a noble gas electronic configuration. So it's isoelectronic. Well, it's isoelectronic with neon. And so how about fluorines? 1s2, 2s2, 2p5. So it wants one electron, right? It wants to be -1 charge, so it has 9 electrons. If it gains 1 electron, then it has 10 like neon as well. So if it gains 1 electron, where's that electron going to go? It's going to go to the 2p to finish it off to make 1s2, 2s2, 2p6. So it makes F-, which is isoelectronic with neon, right? Or if we depicted this with Lewis dot structure, so sodium has 1 valence electron, fluorine has 7 valence electrons. So if you mix these two together, what happens is sodium gives up that electron to fluorine, and you make Na plus, and you make F, which now has 8 valence electrons, F-, right? And the formula for NaF would be NaF. You just need one of each because it's plus 1 minus 1. Okay, so how about calcium? So we said it wants to lose 2 electrons. Which 2 electrons does it want to lose? It wants to lose the outermost, right? This is not calcium. This is magnesium. Let's make this magnesium instead. No, that's fine. Let's make it calcium, so I don't have to change everything. Let's change this. Did I get sulfur right at least? Yeah, 20. Become 18. Yeah. 3s2, 3p6, 4s2. Now it's calcium, right? So what is calcium? 2 electrons does it want to lose? It wants to lose those 2. And then it would be 1s2, 2s2, 2p6, 3s2, 3p6. And it would be Ca2 plus charge, and that's 18 electrons. What else has 18 electrons? Argon does. So it's isoelectronic with argon. And sulfur said wants to gain 2 electrons. So if you mix calcium and sulfur together, what's going to happen is calcium is going to give up 2 electrons to sulfur, and then they both have 18 electrons like argon does. So then that would be S2 minus, so they're both isoelectronic with argon. Or if we drew this as a Lewis dot structure, so calcium has 2 valence electrons. How many does sulfur have? Where sulfur is here in the periodic table, it's in group 4, so it's got 4 valence electrons. No, 6 valence electrons, it's in group 6. So 1, 2, 3, 4, 5, 6. So it's calcium is going to give up 2 electrons to sulfur. So now calcium is 2 plus charged, it's a cation, and sulfur is 2 negative charged, has 2 extra electrons in its outer 3p orbital, so now it's S2 minus. Okay, let's do another of these. So lithium and nitrogen. So lithium's 1s2, 2s1. It's in group 1, right? So it wants to lose 1 electron. So lithium is here. Wants to be plus 1 charged, and nitrogen is here. So nitrogen wants to be -3 charged. So it wants to gain 3 electrons. So if lithium loses 1 electron, that's the one it loses, right? So then it becomes 1s2, and now it's Li plus 1. And nitrogen's 1s2, 2s2, 2p3. Why does it want to be 3 negative charged? Because if it gains 3 electrons here, then it becomes 1s2, 2s2, 2p6, and that would be N3 minus. And now it's isoelectronic with neon, 10 electrons. Lithium gives up 1 electron. It's isoelectronic with helium, which has 2 electrons, right? So how do you make this work chemically? Lithium only has 1 electron to give up, but nitrogen needs 3, so you would need 3 of these. And then each of these atoms can give up 1 electron to nitrogen, and now you have 3 lithium pluses, 3 lithium cations, and 1 N3 minus anion, right? or in Lewis dot structure. So lithium, lithium, lithium with one dot, and nitrogen's got how many valence electrons? It would have 5, right? It's in group 5. So 5 valence electrons. So lithium gives up an electron, gives up an electron, gives up an electron, and then you have, again, Li plus, Li plus, Li plus, and N3 minus. Or if we depicted this in terms of orbitals, right? Lithium's 1s2, 2s1, so it's got that one electron that it's going to get rid of. So 3 lithium atoms, or if I use arrows to represent these, 1s2 is paired, and then in nitrogen, it has 2 electrons in the 1s, and the 1s is ignored here. I didn't sketch it, I just sketched the 2s and the 2 p's. And then the 2 p's have 3, so each of these p orbitals would have 1 electron, right? Because you don't pair them until you have to. And then when this gives away 1 electron, so the 2s then goes away. And now it's just 1s2. It's got 3 protons, but it's only got 2 electrons, so it's plus 1 charged. And then when this gains 3 electrons, then now it's got, still has 2 in the 2s, but now the 2py has 2 electrons, now the 2px has 2 electrons, now the 2pz has 2 electrons, right? Or if we represented that with the block diagrams, then it's going to get rid of this. And this has 1 electron in each to begin with, and it's going to gain 3 more. So we're going to get rid of the 2s, and now the 2p has 2 electrons each in it, right? Okay, and so one more example here. So what about the transition metals? So if we took like iron with 26 electrons. So the transition metals are different. So iron likes to be +2 and +3 charged. So, you know, if you remember, transition metals have multiple charge states, typically +1 or +2 or +3 or +4. So if it is going to be +2 charged, then it's got to get rid of 2 electrons, right? Or if it's going to be +3 charged, then it's got to get rid of 3 electrons. So what you have to remember here is transition metals. Is that they lose the outermost electrons first. So it's not like these other elements where you pick off the electron at the end, like lithium, you pick off the electron at the end, right? Or calcium, you picked off the 4s2 electrons at the end. Transition metals are not like that. They lose the outermost s electrons first. So if you want to lose 2 electrons from iron, it comes from the 4s, not the 3d. So iron plus 2 plus would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, right? But if you want to lose 3 electrons, then you lose the 4s2 first, you lose those 2 first, and then you start picking electrons away from the d orbital. Okay, so you just have to remember that for transition metals, lose the s electrons, the outermost s electrons first, and once they're all gone, then you start taking away from the d orbital, the outermost d orbital, if you need to remove more electrons to get to the right charge. Okay, hopefully that made sense. We will stop there.